It's a great pleasure to be here today and to get to hear about all of the interesting things you guys are working on. So today I'm talking about problems in an area known as multi-reference alignment. First of all, I'd like to acknowledge my collaborators on this project. Matthew Hearn, who was my postdoc mentor in Michigan State, who's now at Citadel, in fact, so no longer at MSU. Cooper Ronis, who's at University of Utah, postdoc there, and Liping Yin, who's a graduate student at MSU. Okay, so today, just to give you a little outline, I'll start off with a little introduction to multi-reference alignment, or MRA for short. Why do we care about these problems? How do we formulate relevant data models in this area? And then the second part of the talk, I'll explore a wavelet-based representation for dealing with these kinds of problems, and an unbiasing procedure for removing some of the effects of the noise corruption. So here we'll look at some theoretical results, some numerical experiments. And then in the third part of the talk, I'll explore how we can, in fact, do better and get more reliable estimates when we know more about the underlying noise model. And then finally, time permitting, I'll give you a little glimpse in kind of a new direction that I'm thinking about going with these things, sort of recasting MRA as a distribution learning problem. Okay. So first of all, and why perhaps this talk fits in well with the theme of the workshop, a little introduction to multi-reference alignment. One of the main motivations for studying these kinds of mathematical problems can be found in cryo-electron microscopy. So this is a novel technology for molecular imaging, which won the Nobel Prize in Chemistry in 2017, as you're probably all aware. And what's the idea here? You want to take pictures of molecules. You have your molecules frozen in a protein sample. You hit them with an electron beam, and then you record, the electrons hit this detector on the other side, and you record an image of your molecules. Okay, so this is really, revolutionized molecular imaging. But there are many really interesting mathematical problems and questions that arise out of considering these kinds of applications. This is a very challenging application for several reasons, one of them being noise. So for example, you might have these molecules which you're imaging, but what you actually see as images out of your microscope might look more like this, like very, very high noise. In one image, you may not be able to see the underlying structure very clearly. So often you're dealing with a very low signal-to-noise ratio, or SNR. Secondly, another thing that makes this very challenging is you don't know in which orientation the molecule got frozen, right? So you have these molecules which could be rotated in any kind of position and shifted around in the protein solution. So for example, if you think about having, well, okay, this is not a real molecule, this is the Mickey Mouse molecule, but if you had something like this that's then rotated in any position, what do you actually see, even without noise, as your images, really depends on the orientation of the molecule. And from all of these images, you want to sort of incorporate, the effects of this tomographic projection to recover what the molecule was. Okay, so that's kind of the second big challenge with this application. And then another big challenge is deformations of the molecules themselves. So for example, things are not always static, so certain molecules will have flexible regions that may sort of flop around, and depending on what configuration it is, even regardless of all the different rotations that are going on, you have different underlying structures that you can be seeing of the same molecule. Okay, so So this is just sort of illustrating some of the many challenges of this application. The basic setup of interest that I will be talking about today when I talk about multi-reference alignment problems is that what are we given? We're given a large number of very noisy observations of a target image or signal, and our goal is to recover a high-resolution approximation of the target. Okay, so this is kind of the broad theme. Noise here, I'm being intentionally vague so that it can mean many things. So noise can mean additive noise, to that sort of graininess. It can mean random translations. It can mean random rescalings or scale changes. It can mean random rotations. So all these different things that can be deforming your underlying object. Okay. So probably the simplest toy model for getting at studying these kind of problems mathematically is known as the one-dimensional multi-reference alignment model. And what's the basic setup? So for now, we're going to simplify our lives and just think about having a one-dimensional signal f, which we're trying to learn. So we have a 1D function f. We want to learn f, but we can't observe it directly. What can we observe? We have this, f will be called the hidden signal, since it can't be observed directly. What do we observe? We observe f randomly shifted or translated by a factor ti, and then plus additive Gaussian noise. So we observe the y's, these noisy signals, and we'll assume we observe a lot of them. So m is how many noisy signals we observe. We'll assume m is pretty large. And our goal is to recover the hidden signal f from all of the noisy observations. Okay, so this classic model, which is the first starting point, includes two key components: random translation and additive noise. And so here we'll assume that these epsilons are independent white noise processes with a variance sigma squared. So sigma squared will really be quantifying how much noise we have in the data. Okay, and then one of the generalizations that I've spent a bit of time thinking about is, what happens when you have other sources of noise, other corruptions that are going on in your data generating process. For example, you may also have scale changes or dilations. So if we can define an operator, L tau, which acts on a function by dilating the function by a factor of 1 minus tau. So here, f of x gets replaced with f of x divided by 1 minus tau. You can think of different normalizations. Here we're looking at an L1 normalized operator. That part's not so important. Just think of these scale changes occurring. And then we think about the data that's being generated as you start with the hidden signal. The hidden signal is randomly translated, randomly dilated, and then also corrupted by additive noise. Okay, so compared with the simplest starting model, now we have the random translations, we have random dilations, and this eta squared will be the variance of the dilation factors, and we also have additive noise, so sigma squared here will be the variance of the epsilons. Okay, so the larger the sigma and the larger the eta, the more noise you have going on.
Sorry for interrupting, but do you know, like in the case of cryo-electron microscopy, what physical phenomena associates to those sources 1, 2, and 3?
So that's a great question, and I'll admit I'm not an expert on cryo-EM, but but I'll take a stab at it. So I think that this additive noise is really like the graininess, in these images, like this measurement error.
Well,
you have
I'm thinking about the scaling and the translation. I'm having trouble mapping the image.
Right. Yeah. So for the translations, you might have, the molecule's not necessarily in the center of your image, right? So it could be appearing down here, it could be appearing up here, and you want, wherever it is in the image.
Physical translation.
Yes, right. Now the scale changes may be a little harder to motivate you may have like slightly different sizes or different, distances, so you might get small scale changes coming in here. Yeah, other questions?
You'll have to introduce the rotation though additionally once you get the multiple.
Yeah, and I'll confess I haven't dealt with it yet, so. So the rotations are difficult and I haven't dealt with them yet. Okay, all right, so here are these three components. So here's a little picture, and again, sort of for the moment thinking about this in 1D, but what's occurring here is you have some underlying signal that you want to learn, right? So this blue thing is F, is the hidden signal, and first of all, what happens is, it gets randomly translated, so it might be, anywhere along this axis, then it gets randomly dilated, so you have these scale changes going on here in the second column in the red. Then we add additive noise. If the additive noise is small, you might still be able to detect where the peak of the signal happens. You might still be able to sort of center and align things. But what we're really interested in is when the additive noise is really, really large, and what you're actually observing are like these purple signals right here. And so basically from a large collection of these purple things, you want to recover one of the blue things. Okay. Okay, and then here is also just an illustration of the model in 2D, even though I'll just be talking about 1D today. But you can think of, what would the 2D MRA model with dilations include. So let's say you have, a picture of a cat which you're trying to learn, but you don't observe this directly. What do you observe? You observe noisy images, so they're grainy, and you also observe, the cat at different amounts of zoom, like really zoomed in, really zoomed out, and then of course maybe it could be, shifted around in the frame to be up in the left corner or right corner. Yeah?
Do they have to be exactly the same, or it could be variation of this cat? Looking for the same, just dilation scale.
Yes, for now. Again, that's sort of like the simplest starting point. Of course, in practice, you might be interested in small variations of these things, but think as a starting point, sort of the same object that's being shifted and dilated and buried under noise. Yeah. Okay. So why consider this model? Okay, so as you pointed out, of course, we'd probably like to be able to handle like slightly different cats, not all of the same cat. So why are we thinking about this model? Basically, we want to get at a way of analyzing the effect of a deformation on the signal input. So we are interested in more general diffeomorphisms where we have an operator which acts on a function f, and how does it act on it? It acts on it by deforming the input. So more generally, we're interested in f, of tau tilde of x, where this tau tilde is some deformation of the input. This is really what we're interested in, but analyzing this in the generic case is hard, right? So this is quite a hard problem if you don't know what's occurring with these deformations. And so you basically have two options. The first is to assume that this deformation is small in some sense. Maybe the norm of the derivative is small. You put some conditions assuming that, these deformations are small under some norm. Or second option, which is what I'll explore today, is you assume that there's some structure to these deformations. So you assume that this tau tilde acts according to a known family of group actions. So maybe you're dealing with translations, dilations, rotations, and you sort of plan your analysis accordingly. Okay, and in the case of translations and dilations is also kind of a natural starting point because it's the case where this tau tilde is linear. So it's in some case the simplest function you could consider if you want to start off analyzing the effects of diffeomorphisms. But even though it's the simplest case, it's actually still quite challenging, and solving the model in itself, even just in 1D, poses a lot of challenges. Okay, So to kind of step back and give you a little more context on MRA and the classic MRA problem where you just have translations and additive noise, there are various approaches for solving classic MRA. So I've kind of summarized some of the main ones here. The first one would be synchronization, okay? And this you can do if the additive noise is not too large. You can try to line things up. So you try to align the signals and then you try to average out the noise. But this is not going to work if the noise is really, really large, like those, purple curves. You won't be able to align things correctly. So you need other methods for the high noise regime. You can try to solve the problem with method of moments. So the basic idea is that you recover the hidden signal by statistics around the noisy data. So you might look at the mean of the expectation of y of x, and you might also look at the covariance of the observed signals, and then from that recover the y. And then a special case of the method of moments would be known as the method of invariance, where even more specifically, you're looking at translation invariant features extracted from your noisy data, i.e. Fourier invariants. And so this third one is what I'll be sort of trying to generalize today. What are some different invariant representations that we can use? How can we use them? Another thing that you can do is expectation maximization algorithms. And these tend to give good results, but are not super scalable when you get really large data sets, and may also not converge to a global maximum. So we'll be focusing on the invariants. I'll be focusing on the invariants in this talk. Okay, so in terms of approaching this problem with Fourier invariants, there's sort of features that you can build of increasing complexity, all constructed in the Fourier domain, and all translation invariant. So, for example, what are some of these features? Well, first of all, just the integral of y, that's translation invariant, right? Shift the signal. Doesn't change the integral. So this is sort of like the most basic thing you can look at. And then building up from there, next would be the power spectrum, where you can look at the modulus squared of the Fourier transform of the signal, because a translation will only affect the phase of the Fourier transform. This will be translation invariant. And then you can also look at the bispectrum, which is, again, constructed from the Fourier transform in such a way that if you have a translation, all of those phase factors will perfectly cancel out, and you'll get a translation invariant representation. Okay, so this is one approach for dealing with that classic MRA problem. Map to the Fourier domain, look at these translation invariant features, average out the noise, and then invert. But when we have more general MRA problems, for example, when we have dilations in the, going on in the underlying data generation, this is not going to work because we get instabilities in the high frequencies. Even actually a pretty small dilation, if you have a high frequency signal, can completely shift the support of the signal. So things get quite unstable. And so we need another way of dealing with these things. We could try computing both a translation and dilation invariant representation. The fear there is that it's not quite expressive enough, or what we will explore here will be staying with the translation invariant representation, but trying to remove the dilation bias from that representation. So how do we unbias the features for the effects that the dilations are having? Okay, so this is transitioning into part 2 of the talk, which is exploring one representation using wavelets that you can try for analyzing this problem. And first of all, let me just put up a little wish list of what we would like in terms of a representation. Ideally, our ideal representation, phi, would have the following properties. First of all, it would be translation invariant. So that's sort of non-negotiable, right? So if F and G are translates of each other, then the features should be exactly the same. The second thing we would like is for the representation to be complete, meaning if the features of two signals match, then the signals are translates of each other. We would like for the bias to be computable, so we want a known bias so that we can try to remove the effect of the bias from the representation. And then finally, we would like it to be invertible, and not just mathematically invertible, but numerically invertible, where we have a tractable algorithm for recovering the hidden signal from the representation. Okay, so we may not get all of these things. We won't get all of them in the first part of the talk, but we will get a lot more of them by the end of the talk. Okay, so first of all, we'll look at a representation that you can use that's based on a wavelet transform. So what's a wavelet transform? You start off with psi, some mother wavelet, say of norm 1, and then you create a whole family of wavelets by dilating that mother wavelet. So psi lambda will be psi dilated by lambda, as you see here. We'll think of lambda as a continuous variable for the moment, and lambda is really measuring frequency. So as you increase lambda, what happens? Your wavelet oscillates more and more rapidly, and so as you increase lambda, you get rapid oscillations. If you look at it in the frequency domain, what's happening is the support of that function is shifting higher and higher into the high frequencies. And then you define a wavelet transform WF by taking, so the wavelet transform acting on signal F is F convolved with psi lambda. Okay. And so then we'll define the following wavelet invariants. So the nonlinear wavelet invariant at frequency lambda can be defined as follows. So I'll use SF for this wavelet invariant representation of the signal F. At frequency lambda, we'll define this as the 2 norms squared of F convolved with psi lambda. And if you want to think about what this is doing in the Fourier domain, what do we have? Well, we have the power spectrum of F integrated, right, against psi lambda, against the power spectrum of psi lambda. So this feature, it's directly computable from the power spectrum, but instead of looking at the power spectrum at a specific frequency, we're sort of binning the frequencies into increasingly large bins and aggregating the information over those bins. Okay, so we're sort of interested in comparing the advantages and disadvantages of these wavelet representations versus working directly with the power spectrum, PF, right, where you just look at the modulus squared of the Fourier transform. Okay, and then to maybe sort of put this into a broader context of some other research that has been done along these lines, so you can use these, you can view these features as the first layer in a non-windowed wavelet scattering transform. And so wavelet scattering transforms essentially cascade convolution and nonlinearities, and they sort of, are, they're similar to a convolutional neural network, but they use predefined filters instead of learning the filters from data. The advantage of this being that you can prove some stability guarantees when you actually know what the filters are that you don't have in general for CNNs. And these representations are translation invariant and were introduced by Malat in 2012. Okay, so we're not really dealing with, layers of these things. We're just looking at these features which would come from a first layer, and we're looking at it under the 2 norm instead of the 1 norm, which was the original context. Okay, so like I mentioned, we're interested in what this, pros and cons of this representation as compared with the more traditional power spectrum. So you can actually show that these representations are equivalent. So for a suitable mother wavelet, you can show that two signals, if their wavelet invariant features are equal, then their power spectra are equal. And if their power spectra are equal, then their wavelet invariant features are equal. So these wavelet invariants are containing the exact same information as the power spectrum. Okay, so the punchline here is that these wavelet invariants, well, they're not invertible, no, because we've thrown away the phase information and we're just basing these features off of the power spectrum. But learning these things, learning these wavelet invariants, is equivalent to reducing the problem to a phase retrieval problem in which you know the power spectrum and you're still trying to figure out the phase. Okay, and you can actually solve a convex optimization problem. After you've learned the wavelet invariants, you can solve a convex optimization problem to recover the power spectrum of F from the wavelet invariants of F. So you can go back to that power spectrum representation if that's what you're interested in. Okay, so here are some results for classic MRA. So these are just sort of mirroring what's already been done in the literature for solving the classic problem by Amit Singer and collaborators, a number of papers along these lines. With the wavelet invariants, if now we look at wavelet invariants, not just the power spectrum. So for the rest of the talk, I'm going to be using this bar notation to denote just an empirical mean. Okay, so py bar is just going to be the empirical average of all my noisy power spectra, and this sy bar, the empirical average of all of my noisy wavelet invariants. And so what you can show is that if you define these estimators for the power spectrum and for the wavelet invariants in a very simple way, just as the mean minus the additive noise level, these are unbiased estimators of the power spectrum and wavelet invariants of the true signal, right? And what is the error that one obtains? You get an error for both representations that looks almost identical. And what do you have? An error which decays like 1 over square root of m, with the sigma squared, essentially like sigma squared over square root of m. Okay, so some observations for the classic MRA model is we get unbiased estimators, meaning the error decays to 0 as the sample size m goes to infinity. Okay, so this is very important, right? We really don't want things to not converge. And the unbiasing procedure is simple and linear. Okay, so what goes wrong if now we consider more general MRA models? So let's say we throw dilations into the mix and we have this generalized MRA model. Random dilations can cause large perturbations in the high frequencies, and these classic unbiasing procedures, which are very simple, will not be sufficient. Okay, so we developed a procedure where we apply a differential operator to the empirical mean to unbias for the dilations. Okay, so what is this procedure? So it looks a little nasty, so I'll call this the order K Wavelet Invariant estimator with differential unbiasing. But what it's doing, it's really rather simple. So this is on the wavelet invariance. You start off with the mean, with the empirical average, and then you subtract off some derivative terms. Here we have lambda squared times the second derivative, lambda to the k times the kth derivative. And then we have coefficients, which depend on the variance, right, of the dilation distribution, and these constant b's, which depend on the moments of the dilation distribution. Okay, so it's just a procedure which adjusts the empirical mean using information about the first k/2 even derivatives, the additive noise variance, the dilation variance, and some constants which depend on the first k moments. Okay.
Yes.
Yes.
I was confused on the previous slide. 'Cause
Yeah.
I see now you have the tildes are estimates of the spectrums. What were the
Yes.
classical estimates that you obtain here that converge? What were those?
You mean these guys right here?
Yeah, in this result. I was curious what the tilde estimates.
Yeah.
Oh, okay. Here they were.
I mean, the big thing here, right, is that this is a tilde for the power spectrum of F, right? So we're learning the power spectrum of the hidden signal F from the Y's, right? So the Y's are noisy. The F is what we're trying to learn. But in the Fourier domain, it works out really nicely. Essentially, all you have to do, because it's translation invariant, you've killed the translations, then you just have to average and unbiased for the additive noise.
All right.
Yeah.
I just missed this. So okay.
Yeah.
Thank you.
No problem. Other questions? Okay, so we did this. All right, so what can you prove with for this generalized MRA model with these wavelet invariants? So you can actually prove with that, more complicated estimator that was just right up here, right? This more complicated thing where we've done some unbiasing based off of the derivatives of the representation. You can prove that the error of those features is upper bounded in the following way. So we have these two terms. We have this eta to the k+2, right? Eta is the standard deviation of the dilation distribution. And then we have this 1/√m term, depending both on the eta and the sigma. Okay, so overall, the error depends on the sample size, the unbiasing order, the noise levels, and we do have some assumptions that we're putting on this dilation distribution, but they're pretty minimal assumptions. It's mean zero, symmetric, and bounded. So what is kind of the main point at the end of the day? We like this term, right? This has an error which is decaying to zero as m grows, but we don't like this term. Unfortunately, we are stuck with some bias here. So if we look at sort of the error decomposition of what's going on, we have a variance term, which we're pleased with because it decays nicely, but we have a bias term which scales like eta to the k+2 times some constant. Okay, but we have improved things. So if we didn't do any unbiasing procedures, we would have a bias that was like eta squared. With this unbiasing procedure, we've reduced that bias down to eta to the k+2. So if we decrease the bias, and you might want to sort of just keep increasing that k to drive the bias to zero. That was our initial hope. And then we looked into these constants and realized there was no way that that was going to happen, right? So that after a certain point, you should just stop because the constants also grow very rapidly in k. But for sort of a moderate size k, you get a big improvement. Okay, so just sort of a picture illustrating the error decay. So this is for a high frequency signal. We've got additive noise and dilations. If you don't unbias, and we're just trying to learn the power spectrum, so if you don't unbias for the dilations, you just do the additive noise unbiasing. This is the decay that you get as you increase the sample size m. On the other hand, these curves at the bottom are what you get from the wavelet invariants. So first, you estimate the wavelet invariants. These are the different unbiasing orders, and then you solve a convex optimization problem to go back to the power spectrum, and then you measure the error on the power spectrum. And what you see is you do see a big improvement, right? You see that these things that the unbiasing procedure is helping a lot, but you do see this plateau, right? Once you hit the bias level, you do see that plateau, and after a certain point, it won't improve. Okay, but to sort of illustrate in practice what you're gaining by the unbiasing procedure on the same high-frequency signal, normally you cannot recover the signal from the power spectrum. In certain special cases you can if the signal is even and the f hat is positive. Normally you can't. In this one you can, and I'm just going to show you the picture so you can kind of visualize what the unbiasing procedure is doing. This is the target signal that we're trying to learn. The purple one, this is what we learn with the wavelet invariants. The red one, so it matches the purple really well. The blue one is what you would get if you just did the classic approach, the additive noise unbiasing only. You see it's very deformed, and this is what their power spectra look like. So what you actually observe is this blue curve, but the power spectrum of the true signal is that purple one, right? And the red is the wavelet, and what you get from the wavelet invariants as the estimator. Okay, so there's pros and cons, like for everything, there's pros and cons. So the advantage of the previous approach is we made minimal assumptions on this distribution of dilations, and we only needed to know what the first few moments of that distribution was. The disadvantage, which we saw very clearly in that plot, is the plateau, right? After a certain point, we're going to be stuck with some bias that we just can't decrease, even if we can keep observing more and more signals. So we saw it was impossible to obtain an unbiased estimator in this case. And also, I didn't talk about this a whole lot, but even though the wavelet invariants are mathematically equivalent to the power spectrum, actually doing that inversion numerically is a bit unstable and tends to blow up the air. So we're not real happy with that from a numerical perspective. So the question we started to think about is, well, what if we know more? What if we know exactly what the dilation distribution is? Could we solve the problem in that case? Is it even possible to define an unbiased estimator? So for simplicity, we're going to start off assuming a uniform distribution, so that the dilations follow a uniform distribution. This is not really so critical. The critical thing is just that you know what it is, like you have that information. Okay, and so kind of the whole approach is based off of the following observation. In sort of this infinite sample limit, if you think about, well, let's just say we have as much data as we want. M is going to go to infinity. Then, if M goes to infinity, then you really, you know this thing, or you have a very good estimate of it, what the expected value of Py, this is the noisy, remember y is noisy, so the expectation of Py, you would be able to essentially observe this, and what you can show is that this plus some omega times the derivative of that with some additive noise and biasing, if you compute this and then you apply the inverse of this operator L, where L is the difference between two dilation operators, then you actually recover the power spectrum of the noisy signal. Okay, so this form, this exact form, it's very specific to the fact that we're dealing with the uniform distribution. This comes, this is based off of knowledge of that dilation distribution. But what the basic idea is that we have access to this expectation of P of y as m goes to infinity. In the infinite sample case, we can actually recover the target representations by inverting that density-dependent operator. And then the question becomes, well, what about the finite sample case? Do things stay nice if we approximate those things well? And the answer is yes. Right? If you have a large M, everything is well approximated, and it works. Okay, so the idea is that we're going to approximate this thing that the estimator is based off of, the expectation of Py, by the empirical mean, smoothed out. This is not a differentiable thing, and we need to differentiate it, so we're going to smooth it out with a little Gaussian filter. But if we do that, so we define a new estimator of the power spectrum, this PF tilde, in the following way. This is all constructed just from the empirical mean of the power spectra, right, convolved with a little filter, and we construct this term, and then we apply this L inverse. Thank you. I have 10 minutes. I'm definitely going slower than I anticipated, but I'll speed it up. Then what you can show is under mild conditions on the power spectrum, the mean squared error of this estimator scales in the following way, okay? But probably more importantly is not so much this, but it's what do you get if you choose the width of that Gaussian filter in the correct way. And so let's say, assuming that we scale things appropriately, what do we get? We get a mean squared error that we're pretty happy with, because you have this eta squared over m, and then sigma fourth over m to the 2/3. So you have this really nice decay, an unbiased estimator going with an error going to 0 as you increase m, which we did not have before, right? So I guess especially after our previous results, we were excited about this. Okay, so what's the key point? So we get an unbiased estimator for the power spectrum. And we call this procedure inversion unbiasing. So this inversion unbiasing procedure gives us an estimator with an MSE decaying like 1 over m to the 2/3. And you could do the same thing on the wavelets, like you could do that same unbiasing procedure on the wavelet invariants, but in our experiments it wasn't worth it, just because the numerical inversion was too unstable, that we were better off working with the power spectrum directly. Okay, and so then in terms of actually applying that operator and actually inverting L, you don't have a closed form formula for the inverse of that operator, but it's pretty easy to do this part numerically. So this estimator can be easily obtained by solving this convex optimization problem where we're basically trying to match, right? We have a term that we compute from our data. This is our data term. And then we are trying to optimize and find the best G, the best power spectrum, that when we dilate it, it matches what we observe in the data. And that's pretty stable and easy to do. Okay, so just to kind of give you an idea, so of the improvement that this is over the differential unbiasing. So here we have kind of a medium frequency signal, and what you see on the left are the results of the inversion unbiasing. So the mean power spectra are the blue, which again are very, very far below the true power spectra of the signal. But with the inversion unbiasing, it's matching the power spectrum very, very well. On the other hand, with dilations that are this large, the differential unbiasing procedure fails. It can't handle dilations which are that large, and it just kind of doesn't really give you anything good. So, okay, and then similar pictures on signal recovery, where you see, ground truth, what you get from inversion unbiasing, how this first approach would fail in this regime, and how, if you don't do any unbiasing, you really fail, right? And also error decay plots, where you may remember before we're always hitting those plateaus, right? So at a certain point, the things plateau, but here we did some experiments on good collection of signals, and our error decay is here in the red, and you see this nice consistent linear decay as you increase m without any plateauing effects. Okay, so, all right, so what about full signal recovery? So far we've discussed recovering the power spectrum of the hidden signal, but in general, the power spectrum is not invertible, can we extend this procedure to operate on higher order invertible Fourier invariants? Okay, so in my last few minutes, I want to talk about this a little bit. Okay, I've been talking a lot about the power spectrum today. So what is the power spectrum? One way you can think about it is as the Fourier transform of an autocorrelation function. So this is like the Fourier transform of the second order autocorrelation function. If you make this little function a2 of t by integrating y times y shifted by t, you get the autocorrelation function. The power spectrum is the Fourier transform of that. The bispectrum, which is our third order, it's the Fourier transform of the third order autocorrelation function. So another way you can think about it is, you have this triple correlation function, A3, T1, T2, which is defined like this. If you take its Fourier transform, you get these features, which is the bispectrum. And in principle, you can keep going. You can define higher and higher order autocorrelation functions. You can take their Fourier transforms. And so you can get sort of richer and richer, more expressive translation invariant features with this procedure. In general, we don't usually need to go past the bispectrum because the bispectrum is invertible under pretty general conditions. So this is usually enough. Okay, but this gives us kind of a principled way of obtaining increasingly expressive translation invariant features. Okay, so the key observation for kind of extending what we've done to higher order Fourier invariants is that when you have a signal which is dilated, if you look at the Fourier transform of the nth autocorrelation function, it's only affected in the radial variable. That's how dilations operate. They're only going to operate in the radial variable. And so you can develop a general strategy, which is, look at, the Fourier transform of this nth order autocorrelation function, or maybe just think the bispectrum. Write the bispectrum in polar coordinates, apply this inversion unbiasing procedure just in the radial variable, and then invert the representation. Okay, and so this actually works out, and it works out really in very similar ways to what I already presented to you on the power spectrum. You can do the same thing on the bispectrum. You just gain, the invertibility that you didn't have before. So you have a, slightly more complicated estimator, but the idea is the same. You construct this estimator from your data and from knowledge of the dilation distribution, and then what do you get at the end of the day? You get an error which decays exactly the same way in M, and a little bit worse in sigma, right? If your sigma is large, because you're using a higher order feature. Okay, and here's like a picture kind of illustrating what this unbiasing procedure is doing on the bispectrum. Here's your here's your ground truth. Here's your ground truth signal. Here's what you actually observe from your data. Notice how the support is even like totally distinct, right? It's way off. And then here, this is the result of the unbiasing procedure. You've really successfully pushed it back out to match what the ground truth is. Okay, and so just a small comment on inverting the bispectrum. So we've essentially shown we can reduce the problem to inverting the bispectrum, and the bispectrum is invertible under fairly general conditions. Here's a collection, there's various methods for this. Here's a list of some of the different algorithms that you can do. Okay, so I think I'm just about out of time, so I don't think I'm going to get to the fourth part of my talk, but that's fine. So I'll just kind of wrap up with what are some of the future questions that we're interested in related to this kind of inversion unbiasing procedures. What about other dilation distributions? Is the uniform distribution special? Can we do this for a broad family of distributions? We expect that we can, so we think there's a general principle here where if you know the dilation distribution, you know what this operator is, and if it's invertible, you can once again recover the Fourier invariance of the signal. Okay, so this is still right to be worked out, but we think that there's a general principle at play here that would extend. Then the really important question, or the really interesting question becomes, well, what about learning the dilation distribution? And this would be, of course, critical if you wanted to do any of these methods on real data and real applications where you don't know what that distribution is. So if we don't know it, but we need to know it in order to unbias the representations, what do we do? And one approach that we're thinking about is actually going back to the wavelet invariants, not for learning the hidden signal, but for learning the dilation distribution. Key observation there being that if we look at these wavelet invariants at an exponential scale to what we had before, then the dilations show up as a translation. So then if we have this f, which was dilated by tau, that dilation now shows up as a translation in the wavelet invariant representation. So a possible approach would be to learn these wavelet invariants by solving a non-Gaussian classic MRA problem, and then learn the dilation distribution by solving a deconvolution problem. So those are some of the things we're thinking about. And sorry, I didn't get to this, but it's kind of a standalone thing. Also interested in recasting this whole MRA problem in the context of distribution learning, where you're not like, you don't observe continuous signals, you just observe like observations from underlying distributions, which are shifts and rescalings. Okay, thank you very much.
Thank you.